Okay, this is AP Podcast 7.2, and we're going to talk about Le Chatelier's principle. So the first thing that you need to know about this principle is that it says if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. This is just like what we were looking at in the lab that we did. We stressed the reaction in different ways, and we saw a color change that indicated which direction the reaction went in order to kind of adjust to that stress that we imposed on it. And then when you're doing these, you need to remember that when we have a solid, it does not affect the equilibrium. So not a solid like the salt that you might be thinking that we used in the lab. Remember, the salt was actually chloride ions that were having an effect. So once we put it into the solution, it became aqueous. We're talking things that are solid, they're not aqueous. It's not going to have any effect on the equilibrium. Okay, there's three ways that we're able to change the equilibrium in a reaction. We can change the concentration, the pressure, or the temperature, and we're going to talk about each of these three ways individually. So practice problem number 1, change in concentration. It says predict the shift of the equilibrium position in response to each of the following changes in conditions. So if we look at this, we have As4O6, we have solid carbon, and then we're getting the arsenic gas, and we're getting carbon monoxide. So what we're going to do here is we're going to say in situation A, what happens to the equilibrium, which direction is it going to go if I add carbon monoxide? So if I look at this and I just start adding more carbon monoxide gas, I keep pumping it into this reaction, what we're going to see is that in order to kind of compensate for the stress that we're applying, if I have more of this, the reaction is going to shift to the reactants. It's going to go left. It's going to try and compensate for all of this that we're adding that's now extra, and it's going to shift it back towards the reactants. So this first one here is that it's going to go toward the reactants. And if you want to draw an arrow, you can as well. Okay, if we have the addition or removal of solid carbon. Well, we just said that a solid does not affect equilibrium. So if I add or remove the solid carbon, it is not going to matter. So this is going to be no effect. It's not going to do anything. And then the last thing is the removal of arsenic. Arsenic is a gas right here. If we start removing it, so we're taking it out, it's going down, what we're going to see is that this reaction will shift in a way that it's going to try and replace the arsenic that's leaving. So in this case, it's going to shift toward the products. So when you're removing a substance, you see the equilibrium shift towards what you're removing because it's trying to replace what's being taken away. When you're adding things, you see the equilibrium shift away from what you're adding because it's trying to kind of distribute all that extra that you have, and it's going to shift away from that. All right, the second way we can change equilibrium is to affect the pressure. And there are three ways then to that we can change the pressure in a system. And that's containing gaseous components because we have to have pressure and there has to be gas. You can either add or remove gaseous reactant or product. You can add an inert gas, and an inert gas is one that's not involved in the reaction. Usually it's a noble gas. And then we change the volume of the container. Those are all different ways that you can change the pressure. The first situation, the addition or removal of a reactant or product, that's what we just talked about in the concentration section, so we're not going to talk about it again. The addition of an inert gas increases the total pressure, but it's not going to affect your equilibrium of the system. And the reason it doesn't affect the equilibrium is because an inert gas is non-reactive, and since it doesn't react, it doesn't participate, and therefore the equilibrium's not going to adjust. So if you add an inert gas, nothing's going to happen to the equilibrium, nothing's going to shift. The last way you can change pressure, though, is to change the volume, and that's the one we need to focus on because we haven't talked about it yet. A change in volume equals a change in your concentration and your partial pressures. So when the volume is reduced, the system responds by reducing its volume. The reaction is going to shift toward the side with the fewest gaseous molecules. So practice problem number 2 says predict the shift in equilibrium that will occur for each of the following processes when the volume is reduced. So we're taking the volume down, we're making it smaller. And if I look at the first reaction here, I have a total of 1, that does not count because it's a solid. So I have 6 gaseous molecules on this side, and I have none on this side because that doesn't count either. So if I'm reducing the volume, this thing is going to shift toward the side that has no gaseous molecules in this case. So this is going to shift toward the products because there are no gaseous products. It's going to shift to the side that reduces the number of gas molecules in the air. So it's going to shift towards the products. It's going to go right. In this question, we have 2 total gaseous products on this side, and I only have 1 over here. So again, because this is the side that has the fewer number, we're going to see a shift toward the products, and it's going to go right. So when you're decreasing the volume, you want to shift to the side that has the fewest number of gaseous molecules. And when you're increasing the volume, you're going to see it shift the opposite way. It's going to shift to the side that has the most gaseous molecules. The last thing is changing the temperature. That can affect your equilibrium. Changing pressure and concentration alter the equilibrium position, but they're not going to change what that constant K is. That will still stay the same. Changing temperature, though, changes your equilibrium constant. If you think of the rate constant that we talked about earlier in the previous unit, we know that the rate constant didn't change unless we changed temperature, and the same is true for the equilibrium constant. What we're going to do with the change in temperature is we're going to talk about an enthalpy, a change in enthalpy. If the change in enthalpy is positive, the reaction is going to be endothermic, and we're going to treat energy as a reactant. Because we have to put energy into the reaction to make it go, that heat and that energy is going to be a reactant. If your delta H is negative for the reaction, that means it's releasing it, it's exothermic, and then in that case we're going to treat the energy or the heat as a product. Anytime you're increasing the temperature, you're going to increase the energy in the system. So our question with that says, for each of the following reactions, predict how the value of K changes as the temperature is increased. So if I do this and I look at my reaction I have here, here's the delta H for this reaction. This is a positive delta H, so that tells me that this is an endothermic reaction. So the energy or the heat, I'll put energy here, is going to be treated as a reactant because we have to put energy in. So when I do this, it says predict how the value of K changes as the temperature is increased. Well, if I increase the temperature, I'm going to be putting in energy, which is a reactant. That means the reaction is going to shift to the product side. So if I shift right toward the products, we know products go on top in our K expression. We have products over reactants. So if I'm shifting to the right, I'm going to be increasing the products, and I'm going to be decreasing the reactants. So my K should get bigger, because this should go up and those will go down. In this one right here, we're having an exothermic reaction because it is a negative delta H. So with an exothermic reaction, we treat energy as a product. So in this case, if I start putting more and more energy in, this reaction is going to shift back toward the products. So a new equilibrium is going to be established because we're shifting left. And that means that our K should get smaller. We're going to increase the amount of our reactants and decrease the products. So in this case, the bottom is going to get bigger, the top is going to get smaller, K should also get smaller. And then the last thing we're going to do is the summary question. What I'd like you to do is pause this for a second, and I want you to look at the reaction and the delta H that's given, and I want you to see if you can fill in what you think the shift will be, and then see how you did as compared to what I talk about when I go through it. So here we go. If we add the N2O4, and the N2O4 is right here, it's a reactant, I'm going to add it. It should shift to the right to compensate. So I'm just going to draw an arrow to the right. It's going to shift to the right, and I'll do an R2. The addition of the NO2, if I add NO2, it should shift back to the left to kind of equal out what's going on there. So in this case, it's going to shift to the left. The removal of N2O4, anytime we remove things, you see the equilibrium shift that way to kind of replace what's being taken away. So when that happens, it's going to shift left. If you remove the NO2, it's going to shift right. It's going to try and replace what you're taking away. Addition of helium gas. Well, helium is an inert gas, so this is going to have no effect. This isn't going to change anything. Those inert gases don't do anything. If you decrease the container volume, when I'm looking at decreasing or increasing volume, that's when you have to look at total number of moles of gaseous molecules. So when I do this, I have 1 on the reactant side and I have 2 on the product side. So if I'm making the volume smaller, it shifts to the smaller number of gaseous molecules, so that would be a shift to the left. Increasing it, it's going to shift to the side that has more, which is to the right. And then an increase in temperature. This is an endothermic reaction, which means energy is a reactant. If I increase the amount of energy that's going in, it's going to shift to the product side. So this is going to shift right. And then it must do the opposite if I decrease the temperature, because I'm going to be taking away a reactant, so it's going to shift back towards the reactant side. So this one's going to go left. All right, that is it for this podcast. Just make sure you're comfortable describing what's going to happen to that equilibrium as we add and remove different things, as we change the conditions that are surrounding the reactions.